Alright, we're in section 5.7 where we are applying the fundamental theorem of algebra. The fundamental theorem of algebra states that if you have a function which is a polynomial of degree n, when n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. Corollary means that if f of x is a polynomial where degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated x times is counted as x solutions. Excuse me. So basically what that's telling us is if we look at a function, or a polynomial function for that matter, and we're trying to determine how many zeros there could possibly be for each particular function, we can make the conclusion whether they're real numbers or complex numbers by taking the largest degree in each of our polynomial, and whatever that degree is, that's how many solutions there are, either real or complex. So if I was to look at example A, I got x to the 6 plus 4x cubed plus 2x minus 1. My largest degree is 6, so that means I'd have 6 solutions for A. And then for B, I'd have 3. So what they're asking for us to do in this section, they want us to find all the zeros, whether they're real or complex. So that means we have to take into account complex numbers. So the term I is going to be involved. Now I ends up equaling the square root of -1. During different things we had over the years, they wanted us to, we were talking about solutions that are real or complex, and in previous sections we didn't have the ability to calculate those answers because complex numbers weren't part of our repertoire. But for today's purposes, we will have to take into account complex numbers. Another thing I want you to take and realize is that, say we have I squared, that means that this would end up equaling a -1. So I'll keep that in mind when we are trying to solve our functions. So for A, I got x to the 5th plus 4x to the 4th plus 5x cubed plus 20x squared minus 36x minus 144. So I know that I'm going to have 5 solutions, whether they're going to be real numbers or complex numbers. And so here's what I'm going to do first. I'm going to punch this into my calculator here and go to my y equals, clear this out. And I'm going to go x to the 5th plus 4x to the 4th plus 5x cubed plus 20x squared minus 36x minus 144. And I'm going to graph that. And I got some intersections, so I am just going to look at 1, and that looks like there's an intersection at 2. So what I'm going to do is I'm going to use synthetic division, to help me determine see if 2 is a solution. So I'm going to go 2, put that here, and then it's going to go 1, 4, 5, 20, negative 36, and negative 144. And I'm going to use synthetic division to see if this holds true. So it goes 1, got 2, this is 6, got 12, 17, so that becomes 54. Oh, I'm sorry, 34. My bad. So this is 54. This is 108. This becomes 72, and 144, and 0. So that ends up holding true. So now what I'm planning on doing is implementing what we learned in previous sections about x minus k is a factor of that polynomial. So here our x minus k, our k happened to equal 2. So that means I can put in parentheses x minus 2 because it's a factor of this particular polynomial. And this is our constant, this is our x squared, x cubed, and then x to the 4th. So I'm going to rewrite this here. So it's x minus 2 times the quantity, x to the 4th, plus 6 x cubed, plus 17x squared, plus 54x, plus 72. Okay? Now I can use another value that was given here. So I'm going to use negative 2, and I'm going to use synthetic division on these values. So that means that I'm going to go negative 2, and I have 1, 6, 17, 54, and 72. So again, I'm just going to use my synthetic division. So I got 1, this becomes negative 2, this becomes 4, negative 8, got 9, negative 18, this becomes 36, and I got negative 72 and 0. So that one is a solution. So now I can factor this further. So I got the x minus 2, I got x plus 2, and I can rewrite this equation here as this is my constant, this is my x squared, and x to the 3rd. So now I have x cubed plus 4x squared plus 9x plus 36. Now from here, I can use grouping to help me factor out that portion of the polynomial. So if I were to just sidebar x cubed plus 4x squared plus 9x plus 36, and I were to group these, I can factor out a x squared here, which gives me x plus 4, plus I can factor out a 9, and it gives me x plus 4. So x plus 4 is the same, so I write that down, and I multiply it by x squared plus 9. So that means that I can rewrite this as x minus 2, x plus 2, x plus 4, and x squared plus 9. So now I've gotten to a point where I can use the zero product property to help me solve my real solutions and also my complex solutions. So here, x here would equal 2, which we already proved that. X would equal negative 2, which we proved that too using synthetic division. x then equals negative 4, which actually is one of the solutions on our graph. And if we go to x squared plus 9 and set that equal to 0, subtract 9 to both sides, so I got x squared equals a negative 9. And if I take the square root of this, I have a negative number, so my x would equal plus or minus 3i. So that means that x here equals 3i, and x also equals a negative 3i. I have 1, 2, 3, 4, 5 solutions, which holds true with our degree. So those are our all zero solutions, whether they're real solutions or complex. Let's give another a try. So I have 4x cubed minus 8x squared minus 13x plus 34. So I'm going to punch this in my calculator, so I get 4x cubed minus 8x squared minus 13x plus 38. And I graph that. And I just get the one line. And it looks like it's at something towards negative 2. So let's put negative 2 here. And let's use synthetic division to help us solve this. So I have 4, negative 8, negative 13, and 38. So drop this down, we got 4. Gives me negative 8, negative 16. Gives me a positive 32. Drop this down to 19. And this gives me a negative 38. And it gives me a 0. Okay, so now I can use my x minus k, so that would be x plus 2, because that's a factor of this polynomial. Then this is my constant, this is my x, and this is my x squared. So now I can rewrite this as 4x squared minus 16x plus 19. Now looking at this, this portion of our polynomial, we can solve this one of two ways. We can see if we can reverse FOIL it, and if we cannot, we can then implement the quadratic formula. So I don't think you're going to be able to reverse FOIL those values, so let's just use the quadratic formula. So let's just rewrite that. So it's negative b plus or minus the square root b squared minus 4 times a times c excuse me, all over 2a. So b would be what, negative 16, so this is 16 plus or minus the square root of b squared, which would be 256, minus 4 times 4 times 19 all over 8. So doing some math, I see that I can get 16 plus or minus, so 19 times 4 times 4 gives me 304, so 256 minus 304 gives me a negative 48 divided by 8, and I can factor out a 16 out of there, so that gives me 4. But it'd be like 4i because it's a complex number, so I'm going to say 4i times the square root of 3 all over 8. So if I were to simplify this, 16 divided by 8 is 2, plus or minus 4i divided by 8 would give me 1i over 2 times by the square root of 3. So my solutions here would be, my real solutions would be x equals negative 2, and then my complex one would be 2 plus I over 2 times the square root of 3, and then 2 minus I over 2 times the square root of 3. And those are our solutions for there. 3 solutions, which holds true with our degree. So, last thing we're going to do is, before here we were trying to solve for the zeros. Here we are given the solutions for a particular polynomial, and now they want us to write out the polynomial function with those 0 solutions. Something you have to keep in mind when you're dealing with complex and square root numbers. You have to implement what is called the Conjugates Theorem. The Conjugates Theorem states that if you have a value like a plus bi, you have to make the assumption that a minus bi is also a solution for that particular polynomial. Same thing as if you have a plus the square root of b, you have to make the assumption that a minus the square root of b is also a solution for that particular polynomial as well. So if I look at example A, my values are 7, 2 plus the square root of 3, and then 2 minus the square root of 3. So I have to use my x minus k to implement this. So I have x minus 7 times by x minus, in parentheses, 2 plus the square root of 3, and then also x minus, in parentheses, 2 minus the square root of 3. So if I get rid of those parentheses here, I'm going to have x minus 7 times x minus 2 minus the square root of 3, and x minus 2 plus the square root of 3. So now it's just a case of multiplying this out and getting our polynomial. So I'm just going to pay attention to our last two parentheses. So I'm just going to go x minus 7, and it gives me x squared minus 2x plus square root of 3x minus 2x plus 4 minus square root of 2 over 3 minus square root of 3x plus 2 times square root of 3 minus 3. And I notice that I have a positive square root of 3x and a negative square root of 3x, so those cancel. I have a negative 2 times the square root of 3, and I have a positive 2 times the square root of 3, so those cancel. And I can now implement some like terms. So I'm going to say x minus 7. So I got x squared. I got common factors here, so that's minus 4x. Excuse me. And I got plus 1. So now I just multiply this through, and my answer here becomes x to the third minus 11x squared plus 29x minus 7. Makes sense. I got 3. I have 3 solutions. We're good to go. For B, here I have a 3 minus I. So now, even though they didn't write it down for us, we still have to implement the conjugate rule. So I have to say that it's x minus 8 times x plus 1 times x minus 3 minus I times x minus 3 plus I. Okay? So if I were to get rid of the parentheses here, well, actually I'm going to factor this out, which gives me x squared minus 7x minus 8. And this is x minus 3 plus I, and x minus 3 minus I. Excuse me. So now we're just going to, I'm going to multiply this through. So that gives me, I'm just going to say x squared minus 7x minus 8. And this is x squared minus 3x minus xi minus 3x plus 9 plus 3i plus xi minus 3i plus 1. Okay, so this gives me x squared minus 7x minus 8. That stays the same. So I got x squared, and I have a negative xi and I have a positive xi, so those cancel. I have a negative 3i and a positive 3i, so those cancel. And from the like terms, I get a negative 6x plus 10. And if I were to multiply this through, and ended up getting, was it x to the fourth minus 6x to the third plus 10x squared minus 7x cubed plus 42x squared minus 70x minus 8x squared plus 48x minus 80. And combining like terms, I'll get x to the fourth minus 13x to the third plus 44x squared minus 22x minus 80. And that is finding the zeros for polynomial functions. Hope this helps. Until next time.